Imagine watching a crack in metal close by itself. No welding torch, no heat, no human touch. Just atoms moving backward in time. In July 2023, at Sandia National Laboratories, a 40-nanometer thin strand of platinum was being pulled apart 200 times per second under an electron microscope. Then, something happened that should have been impossible. The crack they were tracking began to heal and kept healing until it vanished completely. The lab fell silent. Every law of fatigue mechanics said metal can only break, never repair. Yet on that screen, the wound in the platinum fused shut. The fracture lines erased like an undo button pressed at the atomic scale. No external energy, no chemical trick, at room temperature. A pure act of self-repair. For metallurgists, it was as if steel suddenly came alive. A decade-old prediction thought to be theoretical fantasy had just unfolded in real time. If this behavior can be replicated beyond vacuum chambers, into real-world alloys, bridges, aircraft wings, and turbine blades, it could end one of engineering's oldest curses, fatigue failure. The question is staggering. Did humanity just teach metal how to heal, or did we finally notice it's been able to all along? For 5,000 years, human progress has been shackled by one problem that refuses to die: metal fatigue. Every bridge, every jet engine, every phone circuit carries the same hidden weakness. Tiny cracks that grow with every vibration, every stress cycle, every gust of wind. We build taller, faster, stronger, but beneath the polished surfaces, entropy whispers the same verdict: eventual failure. The scale is staggering. Up to 90% of engineering failures trace back to microscopic fatigue cracks. In the U.S. alone, those invisible fractures cost hundreds of billions annually. 46,000 bridges, 7.5% of the national network, are already rated dangerously deficient. Each day, 178 million crossings depend on steel that's one unseen crack from disaster. Aircraft aren't immune either. Boeing's Starliner program has lost over $2 billion to fatigue-linked structural setbacks. Metals that once carried astronauts to orbit now threaten to betray them molecule by molecule. From turbine blades and power plants to solder joints in your phone, fatigue quietly eats away at civilization's skeleton. The tragedy is poetic. The stronger we build our materials, the more catastrophic their failure becomes when they finally give out. History remembers their breaking points: the I-35 bridge collapse, the Southwest Airlines fan blade failure, but never the countless microcracks that started years before. And that's why the Sandia discovery hit like a lightning strike. If a metal can spontaneously weld its microcracks shut, if damage itself can fuel repair, then failure stops being inevitable. It raises a daring new question, one no engineer has ever been able to ask with a straight face until now. What if the materials holding our world together could choose not to break? Let's rewind to the moment scientists saw the impossible. Inside that transmission electron microscope, a platinum film just 40 nanometers thick, only a few hundred atoms across, was being stretched and relaxed 200 times a second. The experiment was meant to break the metal, not save it. 40 minutes in, the team noticed a crack stop spreading, then reversing. Under the lens, severed crystal faces began to knit together, atom by atom. What they caught was a living demonstration of a phenomenon called autonomous cold welding, a state where freshly exposed, ultra-clean metal surfaces realize there is no boundary between them and chemically rebond. At the nanoscale, the rules change. Nanocrystalline metals are built from billions of tiny grains, each oriented slightly differently. The thin borders between them, grain boundaries, behave like fluid membranes under stress. When mechanical cycles push and relax the metal, those boundaries migrate. They can shove cracked surfaces together so closely that atoms begin to diffuse across the gap, closing it. No external heat, no glue, just stress converting into repair energy. These observations confirm the theory first proposed a decade earlier by MIT physicist Michael Demkowicz. His simulations had predicted that, under precise cyclic loads, grain boundary motion could favor healing over fracture. For 10 years, it was considered a quirk of computer modeling, until Sandia's microscope caught it happening in real time. The same process has now been seen in copper as well as platinum, suggesting it isn't a fluke of one precious metal, but a mechanism of matter itself. Latent, waiting only for the right microstructure to reveal it. But the implications leave scientists uneasy. If metals can spontaneously heal, what does that say about every law of failure engineers rely on? When that crack closed on its own, it wasn't merely a laboratory curiosity. It was the first signal of a new materials era. For centuries, metallurgy advanced by resisting damage. Harder steels, tougher alloys, stronger carbides. But resistance always reached a limit. And beyond that limit came ruin. Now the strategy flips. Instead of fighting damage, we can make it part of the repair process. Picture what happens when that principle scales. A jet's turbine blades flex thousands of times each flight. If they could rebond microfissures mid-air, maintenance intervals stretch from months to years. Wind turbines in the North Sea could run through storms without costly shutdowns. Bridges could silently heal microcracks each night, their lifespans measured in centuries instead of decades. Even spacecraft, far from human help, could seal micrometeorite scars before the next orbit. This is the birth of regenerative engineering. Machines and structures that recover instead of decay. Maintenance becomes optional. Accidents become preventable. Materials become nearly immortal. The irony is delicious. The same cold welding effect that makes satellites occasionally seize in the vacuum of space may one day be the reason their hulls never fail. And the philosophical tremor runs even deeper. Metals, the symbols of permanence yet inevitability of rust, are behaving more like living tissue. They learn from stress. They heal after injury. The line between the engineered and the organic just blurred. But there's still one catch holding back this revolution, one obstacle standing between lab discovery and industrial reality, and it may determine whether self-healing metals change history or fade into scientific legend. Every breakthrough begins as an anomaly, and this one cracks centuries of certainty wide open. For 5,000 years, metal has symbolized strength and permanence, yet quietly betrayed humanity through fatigue and fracture. In 2023, a hair-thin strand of platinum changed that story. It proved metal can do something engineers never dared to model, repair itself. Still, the path from microscope to megastructure won't be easy. The healing we've witnessed only thrives under nanoscale perfection and near-vacuum purity. Real-world alloys breathe oxygen, bear corrosion, and live under far harsher conditions. The next frontier isn't discovery, it's translation, scaling up nanocrystalline architectures without losing their self-healing soul. Researchers are already experimenting with hybrid metal composites 2.0, embedding repair-ready nanoregions inside traditional alloys. Others are using additive manufacturing to print self-healing lattices, weaving autonomy into every layer. The first commercial uses should appear within the decade, likely in aerospace or nuclear energy, where cost yields to reliability. When it works, engineering philosophy itself will evolve. We'll stop designing for failure prevention and start designing for continuous recovery, cities and machines that adapt and regenerate. Imagine skyscrapers built of metals that mend after storms, or spacecraft whose hulls live as long as their missions. As one scientist wrote, when matter repairs itself, creation never truly decays. The next episode of Future Forge Explorer will dive into exactly how researchers plan to scale these materials from nanometers to megastructures, and whether self-healing alloys could become the backbone of a truly maintenance-free civilization. Because the day metal learned to heal wasn't just a scientific milestone, it was the moment engineering itself started to feel alive.